Thank you for coming. So I hope the screen will be visible. I did use some color in my slides. If you cannot see them, just ask, because we have some connectivity issues. In this case, I was trained like Johannes. He did this. Oh, that might. Okay. So.
But I think maybe you should just wiggle the VGA cable a bit.
Oh, we have an HDMI cable. We tried
okay. Okay.
Don't worry. Okay. So in Johannes' talk, he gave a description of a moduli space that was really hard, and then he used log geometry to make a nicer description of that moduli space. I'm going to try to do something similar. I'm going to do the log geometry description of divisors, or actually piecewise polynomial functions. I think Johannes also mentioned them already. We're going to study them a bit further. I'm going to start with just some illustrations and some examples. And then in the end, I'll refer to some work I did with David in an article, Logarithmic Intersections of the Double Ramification Cycle, which is for the people interested with double ramification cycles and log chow groups. But first, we're just going to do some simple examples. So let's define what I'm talking about. Let's start with the definition of strict piecewise polynomial functions. There's different ways to define this, but I will try to follow the work I did with David. Well, you can just think of a log scheme. You don't have to do it for an algebraic set. And we consider the symmetric algebra over. You probably can't see that this is difficult. Sorry. We have piecewise polynomial functions as the symmetric algebra over the Z algebra, aka the groupification of the Goethe sheet. So I think just to refer to what Johannes calls piecewise linear function, if we just have the degree 1 part of this, then we're basically talking about the groupified Goethe sheet itself. So these are the strict piecewise linear functions. And I think in Johannes' talk, he wrote something like, you can think of this as a beta in some kind of section over the group of the sheet. Well, that's somehow more of the perspective that we're taking, but we also want not just piecewise linear ones, but we want piecewise polynomials, and hence we're taking symmetric algebra. And also a second small warning is that I am not actually talking about the symmetric algebra like this. I'm not talking about the symmetric algebra over the sections of the groupified Goethe sheet. So this would just be merely products of linear ones, strict piecewise linear functions. But we will see an example that we're actually that there will be a difference between these. But as I said, I was going to try and explain everything I did in examples. So maybe we should just get to the simplest example that I have. And that's just a projective plane. So this is in general, you can say, I want to project plane with the toric log structure or with the boundary log structure with respect to say that RP2 has coordinates T0, T1, T2. With the lines, T is 0 is 0, T1 is 0, or T2 is 0. So what do we mean? Luckily, Johannes said we were allowed to not assume that we were log geometers. So I can first explain a little bit what this log structure really is. So what is actually this sheet? Gauss sheaf groupified. So I said you can choose what you like, the toric variety story or the boundary log structure. So let's write them both down. So for the boundary approach, well, what you're looking at is the monoid on some OPU is given by the functions, the regular functions that are actually invertible outside the divisor that we're considering. So in this case, D1, 0, D1, and D2. Inside well, just the regular functions. And for the toric possible approach, I draw here the toric fan. So a small reminder of toric geometry is for such a fan, then for each cone you would get like an Fi open, so a U, and for example with respect to the cone sigma 0, which is not of course are really helpful. This upper quadrant, this would be the spectrum of the K algebra with generators, the integral points of the dual cone. And you can actually see this as, well, the dual cone has two generators. And if you give them very suggestive names, you can name them T1 over T0 and T2 over T0, just so that you can see that this is actually the affine open that we would usually, the standard affine open where T0 isn't 0. Similarly, U sigma 1 can be where T1 isn't 0. And we have open for sigma 2. And what happens for the other cones? So for example, for a ray, say the ray over here is also a cone within your fan. Then we have the spectrum of the K algebra. Well, tau2 dual is in this case actually the entire upper half plane. So this would have 3 generators. One being, we're talking about monoid generators, so one this direction, one that direction, one that direction. I'm sorry, I'm drawing both dual and the normal cone in one picture, but there is an identification. But this would then be the standard affine open of which you do both T0 isn't 0 and T1 isn't 0. So we get for one of these, we get the inverse. But actually in between, we sort of already made a step in which we can describe the log structure or the monoid actually in this case, and that is that the monoid on U sigma 0 is actually just given by this integral points of the dual 0. So that is actually just like the monoid multiples of some generators in.
It's not K star.
Yes.
I mean, you also have K star.
Yeah. What?
How do you have K star? No? Okay.
Sorry.
Also, it's intersected with Z2, right?
Yeah, it's the integral points. I mean, but you mean integral points?
Yeah, sorry. Yes. We're considering monoids in like a plane space. Sorry. And in this case, we have an A and B. Also
now you take bar and you have to remove A at minus A. Right? Because A is invertible now.
Yes. Perfect. Well, clearly you already are very familiar with this example. So you can go a little bit. So I just wanted to make a picture of this because this is a picture that will help you in general cases as well. So just to draw a picture, I'll go to one of the affines. And there is two of our divisors in this affine open. And then we can see that over here, just a random point that's outside our divisors. Okay, we have that your point is both in T0 isn't 0 and T1 isn't 0 and T2 isn't 0. So you're actually in the open corresponding to this monoid. And then we would get indeed the bar of, well, we have a generator of A and minus A, so we should, as was pointed out, quotient all of them out if we're quotienting out the units. So we actually stock 0. So outside of our divisors, we have trivial log structure. If you're just on one branch of your divisor, what happens is you're in the open, well, in this case, the open tau 2, but not in the open U sigma. And we would get, if we would be computing the stock, we would get this, but again, as I was reminding, this quotient out. So we would get a multiple of some variable. And last possible ability in our example is, of course, if you're on two divisors and then to compute the stock, we would actually be looking at sigma 0, and then we would just get C multiple AB. And the reason I wanted to draw this picture is because in the future I might be talking about having one generator for each branch of the divisor going through your point. So I think I've written it down. So this example seems very simple, but in general, if we're looking at smooth log schemes with the log structure with respect to some reduced normal constant divisor, then étal locally, if you're just given by like a coordinate planes or some local coordinates, then we have that the stall at that point is given by a copy of n, or if you provide a copy of c to the number of branches of the boundary divisor going through. So that's actually a rather general description.
Why do you call this piecewise polynomial? Because you cannot, I mean, you can see them as polynomial functions on each cone. That's why, because you kill the linear forms which are vanishing on each cone. Yeah, and then it just means that you're restricting to, you're just looking at the linear functions on each cone. On each cone, you have linear function, and then you take the polynomial. You make it polynomial. So it means that these are polynomial functions on each cone. This is the space of polynomial functions, which are polynomial on each cone.
Yes.
That's why.
I'm not entirely sure that is why we call it piecewise polynomial. It is? Okay.
Yeah. And this is a general. this is a general.
It's not from the moduli spaces that you give it on. Oh, okay, it's the same.
So this is a general picture. If you have something toroidal, for example, if you have the dual cones, then you just do the same thing. If you get polynomial functions which are polynomial on each cone of the dual. Okay.
Someone is nodding very vigorously. Yes. Okay. So. First, this is like this step was called what's our log structure actually, and then what are our strict piecewise polynomial functions. Well, first the strict piecewise linear ones. These are just like global sections of our group-fight ghost chiefs. So you want sections that glue appropriately. I've drawn two different ways of looking at this gluing. In general, from toric geometry. If you want to visualize something, you just take the normal cones, not the dual cones, because you can't really visualize something. But in this case, for each u sigma I, we get an n squared or z squared, but in this case drawn as an n squared, and we have to glue somewhere one of these x's to one of these x's. And this is the formal way of writing that down, because of course we have actual restriction maps between these opens that induce between these opens that way that induce restriction maps. That will tell us how we want to glue our piecewise polynomial functions. So if you would just see a piecewise linear function as well, a section on mu sigma 0, so something times its variable a plus something times its variable b with something in z, and also a something from the monoid on mu sigma 1, and also a something on this one. Then the gluing would mean that some of our this map means that if a is mapped to 0, so the coefficient in front of b remains, this should be the same as x is mapped to 0, so the coefficient in front of y remains. So we get a few of these compatibilities where these coefficients should be equal. So one way to describe one of these piecewise polynomial functions would then be something like this. And here we note that we have 3 coefficients from our 3 rays. That will be useful if we generalize this example a little bit later. And in this case, since the log structure is quite simple, it's not really very interesting. But if you would want to now do a strict piecewise polynomial function, for example, of degree 2, you could look at something like ab plus b squared, xy plus y squared, or u, something like that. Where I use the ideas, we're really looking at polynomials in these variables, because if you would take that to symmetric algebra, see with the generated x, you would actually really be looking at polynomials in x. That this is an idea cloud in a different order. So a more interesting example would be if we have P2 again, because we have to be able to draw it, but if we would take a log structure associated to a divisor that is like an irreducible number cubic, so that actually has a node, then what is your log structure? So in this case, I want to do the branches of your boundary divisors through your point perspective. So here we have 2 branches to boundary divisor. But if you would just be looking outside your point, you have just 1 branch of a boundary divisor. So the diagram of restrictions would look like this. So on U we have 2 branches, and on V we have 1, but these should match up nicely if you check out which boundary divisor went where. So what does this mean? We want something compatible with, let's see, AB. We have 2 maps. A goes to 0, B goes to 0. So this Z multiples, of something X2. So what this would look like. So last example, I had these 2 ways of like really drawing out the restriction map, or just making a picture of the monoid. If you would try and draw what the monoid would look like, you would get a copy of n squared for both A and B. But we sort of want to glue this one, A is 0 and B is 0 together. So if someone is familiar with cone stacks, you would get the co-limits in the category of cone stacks. But I don't assume that you are, so you should just think of this as like a little ice cream horn shaped monoid. Then, so what are the piecewise polynomial functions? So for the piecewise linear ones, we just have something times A plus something times B, but this gluing map means that coefficients are the same, so we actually get into one alpha A plus B. But now something interesting happens in, for example, strict piecewise polynomial functions, because this, like the formal expression A times B, because we took a symmetric algebra and then we took the simplification of that, this is still allowed to be a strict piecewise polynomial function, but this is not a something times A plus B. Something A plus B. So this is where there would be a difference between. Stupid question or? That's okay.
That's a very aggressive question.
That's what I always do. I secretly whisper my questions to someone so that they can determine whether it's okay
I didn't want to
ask
interrupt you. Sorry.
Okay. That's okay. So this is a short introduction to strict piecewise polynomial functions, but what I said was that I also wanted to link it to divisors, so something we know as Chow classes, like the double ramification cycle, the classic algebraic geometry setting. So in order to do that, well, we create a map from the strict piecewise polynomial functions to Chow. So I was thinking that this was only going to be a global, there is a way to do this, but Johannes already introduced it, so this might not be entirely scary. So if you have an element M in your monoid, then you can build an O star torsor. Remember, Johannes wrote down this favorite shorted sex sequence. Our favorite shorted sex sequence with respect to our, what we just get because you are a log structure. And if you take the pre-image here, you get an O star torsor. And then said you fill in 0 to give yourself a line bundle. And we take the dual, which also has a natural section. And then we do the classic algebraic geometry business where we take line bundles, isomorphism classes of line bundles and sections. And we can quite easily make a first Scherm class to get a Chow class. But I was going to just explain this in a small picture, just to be clear what is happening in our very explicit example, namely if we just were looking at coordinate axes, because I tried to convince you that this was not a really weird thing to be looking at if you want to understand log structures, certainly with respect to divisors. So if we just have an A2 with log structure with respect to the coordinate axis, so the log structure is with respect to the function of x, y. So we have like two branches, the y-axis and the x-axis. So what would happen? We would start with an element in your monoid. Well, to give an element in your log structure here, you would simply need, once I've taken the bar, otherwise, yes, there would still be a K star around. You would simply need two numbers. And then the way you sort of the way you identify this log structure to functions invertible outside these divisors, well, you get functions are vertical outside these divisors, you can get multiples of x and multiples of y hanging around. So in our first step, we would get the k star, because that's k star torus are given by x to a, y to b. Then in our second step, we would try and build a line bundle out of this. And we would get the ideal generated by x to a, y to b. But this line bundle is much better known. I think Johannes also wrote this down very quickly, as we are just twisting the line bundle we know with respect to our divisor. And then we take the dual. And then we take the first Chern class, which would just give us a times s we want is b times class 2. Thing to take away from this story is that what we're actually only looking for is we're looking for the amount in the x direction and the amount in the y direction. So we're looking to read off the coefficients of your monoids in the direction of the branches of the divisor. That's what we'll do in the example anyway. And then formally, you can extend this to a map from all strict piecewise polynomial functions. So the first step is that you can do this quite easily if you are if every strict piecewise polynomial function is the product of strict piecewise linear functions, because right now in the above we've described the map for strict piecewise linear functions rather explicitly. And
so just a question that is it possible to characterize the kernel of this map? Because these ones, like to call it maybe global linear functions.
For toric writing.
For toric, yes.
But in general, it can be. In general, it can be. For example, if we could do that, then we would know all relations among boundaries, right?
Exactly, that's what I'm asking.
Yeah.
But what is? Yeah, what is? There's no
well, you know that there are some things in the kernel that describe the entire kernel.
I think Rahul knows the answer in genus 0. So, but
Yes.
beyond genus 0, it seems maybe genus 1 is possible, but in general, it seems just hard.
I think even the statement Rahul knows that genus 0 means genus 0 is not entirely easy either.
No, it's not.
What do you mean relations between boundary divisors? I mean all the powers, or what?
Yeah, so you've got a map from like the.
I mean not relations between divisors. Right?
No, right, indeed, between
because
the,
those are much easier in
yes, no, sorry, I just mean the kernel of the ring, not the kernel of the.
Also, the genus 0 case, I mean, there is like also a classical tropical derivation of that. I mean, you just get these WDV equations, right? Oh,
yeah, sorry, the genus, I was thinking, right, because we're doing strict still. Yes, you're completely right, sorry.
Okay, you have to write the whole dot space. Or?
Yeah, there's an analogous question in the second half of the talk, which has a more complicated answer.
Okay.
But is it true that the kernel of the polynomial is it true that kernel is defined by locally by linear relations? If you know
But I mean, maybe if you take S to be like a nasty Artin fan of even something nice like MGN bar, then there will this map will actually be injective. So it will not have any kernel. So it really depends exactly on the geometry. I mean, we can't just read it off from some combinatorial.
The kernel of which map?
The kernel of the map from strict piecewise polynomials to the Chow group. The kernel of that will in general can be trivial. So it don't have to be any.
It's trivial. Why do it Chow?
What I said is true. Sorry.
which doesn't contradict.
I mean, I guess Rosa will now explain what it means that it's true, but it was true.
But I think it goes in the direction saying that it's true that because locally, because you don't have any.
Maybe we should look at this map in examples, and then You can ask your question again, or maybe afterwards. Yeah. So I just wanted to say, if not every strict piecewise polynomial function is a product of strict piecewise linear ones, in that case, log blowups are going to help us. So if you're not entirely familiar with log blowups, think of this as a blowup in a point with non-trivial log structure. It's a nice blowup, and in that case, we would just define our map as the composites. This map is actually just defined by that we have a map of log schemes between S and its blowup S twiddle. And this is then simple. So this is an example block, and this would just push forward along the blowup map. So we would actually reduce to the case that we already were in. So what happens? Just quickly, this is all copy paste from the previous slides. So quickly back to example 1, the projective space. What would you get if you would apply our practical procedure, just reading off your coefficients in front of your divisor in this case? So if we start with this strict piecewise linear function, this actually yields at, well, this is the coefficient on this open, and that will be the coefficient corresponding to the divisor D2. So we get number of times D2 plus alpha times 1 plus 0 in your child group of D2. And yes, I'm not saying that you cannot write this more easily, because you probably all know what we do with child D2. We just get multiples of some line is scaled in the third power. Our codimension 1 thinks a multiple of line, and codimension 2 thinks multiple of points. But this way of describing it is just to illustrate where it goes along our map. But I also said that log blowups help, and this is an example in which we can very clearly see what log blowups do. So in this case, if you would blow up your plane in 1, 0, 0, this would actually be that you subdivide your plan, so you add an extra ray. And that extra ray, of course, gives us extra restriction maps. So we get an extra here and extra use. But this is actually very much the same story. And what we would get is the strictly linear functions of this form. And then we would get that these, along with our practical procedure to get child classes out of this, we get. Where with the bar, I just mean it's the same divisor, only living on the blow-up, so it's a strict transform of your original thing. In the child group of your blow-up, let's call it as twiddle already. So we have also multiples of your exceptional divisor moving in. But examples in, and I think time-wise, I'm going to go very fast through the next slide, just to say we can very easily also describe this translation from strict piecewise polynomial function on S to strict piecewise polynomial functions on S twiddle, just by the inclusions of our cones and taking like the same function on your subdivision. But this procedure of subdividing will generally help us most in the other example. So this is again a copy paste from example 2, the nodal irreducible nodal cubic. So we knew that for strict piecewise linear functions, we would just have something times A plus B, where alpha in Z as your strict piecewise linear function. And this goes to something times your divisor D. But what is the more important question is what you would do with the A times B, the strict piecewise polynomial function that is not a product of strict piecewise linear ones. So what do we do? And I told you that blowing up will help. So we blow up our space, in particular in this point P, which we've magically already blown up. So blowing up in the point P means we get an exceptional divisor. And when we draw out all the restriction maps, so we have an open W1 where it's just again 2 coordinate axes and over here. And basically what we say is given something on the whole thing, you have something on W1 and that should actually outside of D bar match up with what happens on W2 outside of D bar. And similarly outside of D should match up. So we get these compatibilities. But if you draw the look-like picture, what you actually only did was a subdivision. Here we have an extra ray in our ice cream cone, or if you take the co-limit, we have an extra ray here. And how does this help us? Now, in this case, the strict piecewise linear functions are given by a multiple of, well, we have x plus a multiple of y, and we have u and v. And gluing means that the multiple from x should be the multiple from v, like this. So we have more strict piecewise linear functions in just a number of times AB. Well, again, our map from the original strictly piecewise polynomial functions to its blow up is just, well, inclusions of cones before you take the cone limit, or seeing the same function on the subdivision or however you want to see it. So this comes from quite easy maps. So in this case, we started with AB, that was in the case, and we go to XY, and we go from AB to UV. What we do is something very similar as we saw in the last example. And thus U plus V is just V. And then what do you do with the strict piecewise polynomial functions AB? Well, on the X world, we just A times B is X plus Y. And here it is U plus V plus V. And with this, we can actually do something. So we started with AB. What we got out is totally written as X plus Y, X, U plus V, V. And remember here, our strict piecewise linear functions were of this form we have here. So now we have two of those in the product here. We can just say coefficient 1. So this is a coefficient 1 for, well, the matching for divisor E, and also one for the divisor D bar. And the other one is XB, where we just have a coefficient for one on the divisor corresponds to 0 on the other. Then we map each of these to the chow, and this is a ring homomorphism, so we take a cap product on the other side. So one is just D bar plus E, and the other one is E. And then you do intersection theory on the blow-up. If you intersect D bar with E, you just get those 2 points. E with itself is minus the point. What you map to is just the class of your node. So then you have an idea of where you can send your piecewise polynomial function A. And this is a slide just to refer to my abstract. I was a bit ambitious in my abstract, saying that.
Sorry.
Yeah.
So I'm confused. Do you have to go to blow up, or you can do it directly?
In this case, you have to, because
you have to. I see. Okay.
I only told you what this is in the case that you're doing strict piecewise linear functions,
okay,
or a product of those. And this is not a strict piecewise linear function or a product of them, because these were just like alpha A plus B. And if you would take products of these, you would never get A, B, just itself. So for these expressions, you can just go directly, but with this guy, you needed a world, aka a blow-up, where you can write it as a product of piecewise functions.
So there is a totally different way of constructing the same map which doesn't go via blocks, which is in the paper of Marco and Rupen. So there's a totally different construction of the map which ends up being equivalent and doesn't go via block. So you don't per se have to. But if you want to make this version work, then
have to in my talk, because I've already told you what it does.
If you want to use the machinery that you've seen so far in the talk, then you have to.
So Johannes also drew a picture of this moduli space. So M12 bar, you can give a log structure with respect to its boundary, and there's two boundary divisors. The one with curves of genus 1 is curves of genus 0 is self-intersection, and MD2 is curves of
talk about David saying that if you want to use the one without blocks, then there's some kind of exact sequence of higher child groups. It's a little unpleasant to do. This would make more sense. It's all these blocks.
I was just giving motivation for why you should do it one way or the other. Like this, going through blow-ups means you can give a very explicit description. And Rahul says that if you want to avoid doing blow-ups, you have to do exact sequences and that are on the
higher case, higher travel. We need some subjectivity about the what we're doing.
So just for those of you who know, if you would draw a monoid visualization of this, you would get for this situation, you've seen this before. You would get an n squared, so that's here. And this situation, well, unfortunately, we're stacky, so I've had to flatten my ice cream cone, that's over here. And exercise, but I just wanted to say that with the knowledge we've built and just our toy examples, you can, for example, answer the question that is there a strict piecewise polynomial function such that the image under this composition map phi is actually well, the divisor corresponding to this curve with two genus 0 components intersecting each other. So these aren't completely unmotivated examples. The answer is yes. You should think of something like 3 times v in these coordinates. Anyway, if you get lost during the rest of the talk, you can think about this. Because I just wanted to say in the last few minutes why this is actually useful to have this machinery of piecewise polynomial functions, and you can actually use it to prove some things. So why is strict piecewise polynomial functions useful? Well, firstly, it's quite elegant. I have heard you can give a very nice Pixens formula with it. Johannes described a nice moduli spaces with log language. But in this case, it's also language that allows us to describe what you would mean by tautological in log blowups and log chow. So what I mean with that is there's 2 ideas in that. There is the idea of log chow. That's that we want to consider not just one space, but we want to consider the chow groups of all log blowups of your space at the same time. And yeah, the non-strict version, because maybe you've noticed that I've everywhere said the word strict piecewise polynomial function. That's where you have piecewise polynomial functions on all your possible log blowups.
So log chow group means chow group or all log blowups.
I'll give an extra definition. This is just the idea. Next slide. Wait for it. I also explain why you would actually want to consider all the chow groups on possible log blowups at the same time. That's what I'm going to do first, and then you're going to see a definition. So why would you even do this? So I was hoping Johannes might even say what a double ramification cycle is, but actually it's already here. It's on mg and bar. If you have two vectors, then you can ask the question, what are the curves where if you twist with this vector in certain marked points, xi, when is this actually trivial? And if you ask that question at the same time as asking it for another vector b, that's what we call a double ramification cycle. And this question should be the same if you do it with respect to vector a and vector a plus b intuitively. I mean, it's just a translation of the number of points you twist. So that's over here. And Johannes and David and Aaron Fixton wrote an article saying that this is not true over all of mg and bar. So just taking the intuitive product of two double ramification cycles is not really the answer of the question that you're looking for. So what you want is you want a double ramification cycle which does satisfy the nice GLC properties. And in the article by Johannes, Aaron, and David, they solved it by looking at all blowups. And we prefer doing it with all log blowups. There are quite a few less log blowups. And then I promised to at least show you what the formal definition of log chow is. But you can also stay with the idea of taking the chow group of a blowup and looking at this at the same time. And I also have a formal definition of piecewise polynomial functions, but you just should look at a strict piecewise polynomial function on some blowup and then achievify it in the right way. And these two ideas are quite nicely compatible with what we did. So our maps from strict piecewise polynomial functions, we made maps to the chow. And in these maps, actually, you can get piecewise polynomial functions, your co-limits of your blowups. So these maps actually quite naturally assemble into something that we call phi log. Piecewise polynomial functions actually map to log chow. And then if you would be looking at
I'm sorry, you didn't define PP, no? Because these are the strict polynomial on some subdivision, or some if you take the dual.
You take the sheaf of piecewise polynomial functions. What you do is if you have just a compact space, you take for each open these co-limit of blowups over your open of the strict piecewise polynomials. So
okay, so it corresponds to saying that there is a subdivision such that they are straight from that.
Yes. Okay. So it just means at some height we have a strict piecewise polynomial function, and then all the rest is subdivisions. So and also in this world where we live on all the blowups at the same time, there's also a good double ramification cycle, log dr. And in the paper with David, we showed that this log dr is log tautological. So what does that mean? In the language that we've just built, we mean that this log dr in the log chow of some curve is actually lies in the subring generated by our piecewise polynomial functions. So generated by the image this map by log that we've made. And you need something actual. So you need either an eta class or kappa and psi classes if you're familiar with tautological rings. And I have a feeling that this means that my time is up.
No, it's some organization.
Okay. Well, no, it's a nice wording. This is also the last slide. I just wanted to convince you that this actually solves a few of our problems that we had. So I told you that we wanted the good definition of a double or an R-fold DR cycle. Well, using log DR and just intersecting log DR in this world of many, many blowups, we can actually do that. We can find a good DR, double DR cycle, which is actually tautological. So this is a statement on MGN that the log version is also log tautological. But this was an open statement on MGN. And the thing that we've created is actually GLC invariant. So for example, if you would do this one, this was the motivation that I gave. We want a DR cycle that actually. And then there was a question.
No.
In that case, are there any questions?